Salam and welcome everyone. So today we're going to be working on the question on the screen that says use the values of the relevant standard Gibbs energies of formation from the resource section to calculate the standard Gibbs energies of reaction at 298 Kelvin of the following reactions. You have the first reaction, the second reaction, and the third reaction. Now, I wanted to first of all mention that I'm using the Physical Chemistry Atkins textbook. And in this textbook, they have a research section that has all of the formation that is basically needed for you to solve the questions in the book. So we're told to find the values of the relevant Gibbs energies of formation from the research section. And when we get those values, we should calculate the standard Gibbs energies of reaction at 298 kelvins. Now, the first thing you have to know is I've gone to my textbook and I've written all the relevant information that is needed. And the reason why I'm doing that is so that it's easier for you guys to be able to follow all that I'm doing for this particular question. I'm going to be going back and forth, back and forth, back and forth, so that it's easy for you people to like know what it is that I'm doing, right? So I wanted to say this that before we can go on to start using all of this information on this page, we have to understand the major formula we're supposed to use, which is the Gibbs energy of reaction, like the standard Gibbs energy of reaction is equal to the summation of the Gibbs formation energies for the product minus the summation of the Gibbs energy of formation for reactants. So to begin, I'm going to start with the first reaction. We have 2CH3CHO, okay, gas, plus O2 gas, and then you have 2CH3COOH liquid. Now, I want to quickly mention something so no one is confused. I'm not going to be going back and forth in between pages because I already have this problem solved in my own personal note. So if you need to if you need to like rewind the video and pause it and write out all of the Gibbs energy of formation for each one of the substances or molecules or compounds in this particular question, then I would advise you to do so. But I'm not going to be going back and forth, except if it's absolutely necessary because I have my book. So, anyways, that's just one thing I wanted everyone to note. So you have 2CH3CHO gas plus O2 gas, and then you have 2CH3COOH. Well, applying the formula for the Gibbs energy of reaction, we have going to focus on the product first. So you have the formation, Gibbs energy of formation for the product, 2CH3COOH. Okay, liquid. Let's not forget. It's very important for you to know the phase that you're working with. So yeah, very, very important. So yeah, minus this one right here, which is the Gibbs energy of formation for 2CH3CHO gas plus the formation Gibbs energy of formation of the second reactant, which is just O2 gas. So this is basically how you organize what you're dealing with right here. So now we're going to reorganize again. It's very necessary. It's for you to just have this right here. You bring out the 2 because the 2 right here is a coefficient, right? This 2 right here is also a coefficient. And the coefficient, you cannot find the Gibbs energy of formation of 2CH3COOH or 2CH3CHO, mainly because you can only find the Gibbs energy of formation for molecules or compounds. So what you're going to end up doing is you have to bring out the 2, just say 2 times the Gibbs energy of formation, okay, of each one of the compounds. So that's how you properly arrange it. But I like to do it step by step so everyone is on the same page and there is no confusion. So I'm going to do the same thing here, 2 times the Gibbs energy of formation of this compound. So 2CH3CHO gas, okay, plus this one has no coefficient is 1, so no biggie, so that will be O2 gas. So yeah, that's basically what's supposed to be done. Now we can start to substitute. Like I said, I'm not going to be going back and forth in between these pages to write it all down. So if you need to pause this video and write all of this information, since I've already done more than half the work where you have like gone to the research of the textbook to give you guys these values, you can pause this video, write those values down, and then you can start to substitute. So you have this information right here. You have 2, okay, times the Gibbs energy of formation for CH3COOH for me. According to our research section, we have 389.9 kilojoule per mole, okay, minus right here 2 times the Gibbs energy of formation for CH3. Sorry, this is a mistake. For CH3CHO gas, 128.86 kilojoule per mole plus the Gibbs energy of formation for oxygen is just simply 0 kilojoule per mole, just zero. So yeah, we've done it for the second one. Now we have this. So the Gibbs energy of formation, the Gibbs energy of reaction is now going to be 2 times 389.9 kilojoule per mole is just simply 779.8 kilojoule per mole. Okay, minus 2 times 128.86, which is just simply 257.72 kilojoule per mole. So that's basically how it's done. So we're now going to input our information in the calculator. 779.8 minus 257.72 would give us 522.08 kilojoule per mole. So this is basically how this is done. Now let's not forget that when we're doing our work, we have to look at the proper number of decimal places. And we see that the initial information in the question, one of the Gibbs energy of formation is 1 decimal places. So it has the lowest number of decimal places. So we have to put our answer in that number of decimal places. So we have this answer here to be 522.1 kilojoule per mole. And this is basically the answer to this question. So now let's go to the second reaction. The second reaction is Ag, 2AgCl, solid, plus Br2, liquid, and then 2AgBr, solid, okay, plus Cl2, gas. So we have all of this information. Let's not forget the general rule is this one right here. We know that the Gibbs energy of reaction is just the summation of this is the coefficient, by the way, for all of you who don't know what this V stands for. It stands for the coefficient. So, sorry, let me change back to purple. So you have the Gibbs energy of formation, okay, for products minus the Gibbs energy, the summation of the Gibbs energy of formation for reactants. So that's basically the general formula for the Gibbs energy of reaction. So we have that, we have our reaction. Let us organize. So we have this one right here. We're going to first of all focus on the product. So you have the Gibbs energy of formation for the first product. So that'll be 2AgBr, solid, okay, plus the Gibbs energy of formation of the second product. So that would be Cl2 gas, okay, minus the Gibbs energies of formation of the first reactant, which is changing the Gibbs energy of formation for the first reactant, which is 2AgCl solid, okay, plus the Gibbs energy of formation of the second reactant, which is bromine liquid. So yeah, Gibbs energy of reaction. So reorganize again. So we have 2 times the Gibbs energy of formation, okay, of AgBr when we reorganize solid, plus this one doesn't have any coefficient greater than 1, so we're just going to rewrite it here. So chlorine gas, then minus here we have a coefficient greater than 1, so we have 2 times Gibbs energy of formation of AgCl solid, plus Gibbs energy of formation for bromine liquid. So yeah, that's basically it. So the Gibbs energy of reaction would just be us substituting. So 2 times the Gibbs energy of formation for AgBr. Looking at the resource section, we have negative 96.90 kilojoule per mole. Okay, plus the Gibbs energy of formation for chlorine gas. Well, that's just simply 0 kilojoule per mole. Okay, so that we're done with the product side. Now we're going to deal with the reactant side. 2 times the Gibbs energy of formation for AgCl solid. We have that to be negative 109.79 kilojoule per mole. And we have the Gibbs energy of formation for bromine liquid to just simply be 0 kilojoule per mole. Gibbs energy of reaction is just 2 times negative 96.90 kilojoule per mole. That's negative 193.8 kilojoule per mole. Okay, so just this. And of course, plus zero, so we don't have to focus on that. So this is the product side minus 2 times negative 109.79 kilojoule per mole. We know that to be 219, okay, 0.58 kilojoule. I'm about to write kilograms, kilojoule per mole. Of course, plus zero, we don't have to write that down. So you have, sorry, that 2 times negative 109. So it's going to be negative 219. So just rewriting this, gives energy of reaction becomes negative 193.8 kilojoule per mole, okay, plus 219.58 kilojoule per mole. You just simply put this information in the calculator to get 25.78 kilojoule per mole. And this is basically the answer to the question. Now, looking at our question, we're going to see that the lowest number of decimal places based on the values that we solved in this question, meaning the values that we were given at the beginning. So the formation for AGBR and the formation for AGCL, the lowest number of decimal places is 2 decimal places, and our answer is in 2 decimal places. So this makes this answer here our final answer. We don't have to manipulate anything. So yeah, that's basically how it's done. Now the third question, let me just do it on the last page. We have the equation Hg mercury, so HGl, okay, plus Cl2 gas, and we have HgCl2 solid. Let's not forget, same old information. We know that the standard energy Gibbs energy of reaction, the formula is the summation of the Gibbs energy of formation for all of the products, okay, minus the summation of the Gibbs energy of formation for all of the reactants. So that's basically how it's done. So the Gibbs energy of reaction is going to be equal for the products, we're going to do the product first. So let me just write that down. So you have the big bracket. So you have the Gibbs energy of formation for HgCl2 solid minus the Gibbs energy of formation for the reactant. So you have Hg liquid plus the Gibbs energy of formation of the other reactant, which we have to be Cl2 gas. Okay, so we've basically organized. You can look at this question, this particular part of the question. You can see that we don't have to organize twice because the reactant does not have a coefficient greater than 1, or neither does the product have a coefficient greater than 1. So HgCl2, every single one of those compounds or molecules have their coefficients to be 1. So we don't have to rearrange further. We can just simply substitute. So you have this right here. So you have it gives energy of formation for HgCl2 according to the resource section of our textbook is just negative 178.6, okay, kilojoule per mole, okay, minus it gives energy of formation for HGl, which is just mercury liquid, is 0 kilojoule per mole, okay, plus the other product, which is Cl2, that gives energy of formation for chlorine gas is also 0 kilojoule per mole. So what's just going to happen is just us just having gives energy of reaction will be negative 178.6 kilojoule per mole minus 0, which is just simply us just getting this answer, which is just negative 178.6 kilojoule per mole. So this is basically the answer to this question. So if you have any questions, put in the comment section. I'm going to be doing a bunch of questions in the Physical Chemistry Atkins textbook, the 11th edition. And there are a bunch of questions, like the B part of this particular question is also going to be done in another video. So make sure you follow and subscribe, and make sure you follow my playlist on physical chemistry in order for you to get the best physical chemistry resources and information. I also wanted to mention that I'm a tutor for students who want to succeed and be the best version of themselves while in school and outside of school. So if you're trying to succeed in all your STEM related courses, whether you're in middle school, high school, or college, make sure you email me at shohabitutoring@gmail.com. If you also would want mentorship as you navigate your academic life, also email me at shohabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.